Hello guys, welcome back. So today's subject is network analysis and the topic is about Thevenin's theorem. So Thevenin's theorem states that any two-terminal linear bilateral network containing a number of voltage sources and resistance can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistance RTH and load resistor RL, where VTH is equals to open circuit voltage VOC between terminals A and B. It is also called as Thevenin's voltage, and RTH is equals to the equivalent resistance of the network as seen from the two terminals A and B, with all the other voltage sources replaced by their internal resistances. It is also called as Thevenin's resistance, and RL is equals to any load resistance. So Thevenin's equivalent circuit is nothing but a combination of Thevenin's voltage source VTH in series with RTH Thevenin's equivalent resistance, which is similar to a particular particle voltage source. So in the step 1 is to determine the current through load resistance RL, temporarily remove the load resistance RL from the terminals A and B as shown in the figure. In step 2, find the open circuit voltage VOC between the terminals A and B by keeping all sources in their original position as shown in the figure B. So total resistance we'll get as R is equals to R1 plus R3, and current through R3 we'll get I3 is equals to V by R, that is equals to V by R1 plus R3, and voltage across R3 is VTH is equals to I3 R3 is equals to V by R1 plus R3 into R3. For the determination of RTH in the step 3 we'll see find the Thevenin's equivalent resistance RTH of the network as seen from the terminals A and B as shown in the figure C by replacing the voltage sources by their internal resistance, or short circuit it if the internal resistance is not given, and current sources are open circuits. As R1 and R3 are in parallel and this combination is in series with R2, therefore RTH is equals to R1 parallel to R3 plus R2, that is equals to R1 into R3 divided by R1 plus R3 whole plus R2. So in the step 4, we will draw the Thevenin's equivalent circuit by replacing the entire network by signal Thevenin voltage source VTH in series with Thevenin resistance RTH as shown in the figure D. So in the step 5, we'll connect the load resistance back to its terminal A and B from where it was removed as shown in the figure E. And so in the step 6, we'll determine the current flowing through RL by applying Ohm's law, that is IL is equals to VTH divided by RTH plus RL. And in step 7, the potential difference across load will be VL is equals to VTH divided by RTH plus RL into RL. So this is the problem under Thevenin's equivalent theorem, and the circuit is given. So in the step 1, we'll find VTH by applying KVL to the loop 1, and we'll get I1 as 2A, and VTH is equals to VA minus VB, and we'll get VA is equals to 12 volts, that is equals to VTH. And in the step 2, we'll find the value of RTH, and we know that RTH is equals to VTH by IN, that is equals to VTH, and we know the value of VTH, that is 12, and IN is equals to 0.882, and by dividing that we'll get 13.60 ohms, and then we'll find the value of IN by short circuiting A and B. And by applying the loop analysis for I1 and I2, in loop 1 we'll get the equation as 10 I1 minus 4 I2, that is equals to 20. This is equation 1. And in loop 2 we'll get the equation as minus 6 I1 plus 16 I2 is equals to 0. And by substituting these values we'll get I1 as 2.35 and I2 as 0.882, and we'll reconsider the circuits as given below. So thank you for watching.